Hello community, so great that you are back. Yeah, today we talk also about chain of thought. You say, my goodness, what a pleasure to be here at the Discover AI channel where we have a look at the latest research paper. Yes, and we go on because you remember just 3 days ago we had here this video where I showed you that AI thinking breaks here. We do not yet have the mechanisms implemented in our AI systems. And I showed you with this video that even with chain of thought, this is not anyway an AI safety feature. And my last video was here about the chain of thought here with a code interpretation and the problems we encounter with this. And today we have video number 3. So let's start. You remember in this video here, the lie we built chain of thoughts, we have 3 chain of thought traces. We have the internal one, the hidden one, then we have the interleaved one, regarding here the tool calls, and then we have the synthetic, very nice generated Saga external chain of thought that they show us. And I showed you that the ability of the LLMs to lie is massively different if you have an internal, if you want chain of thought reasoning trace here in Claude Sonnet 4.5, or if you go to the external, hey, it can lie at the external chain of thought, no problem at all. And if you know, we stopped here, those 3 videos here on this image, and I explained to you here, okay, this is our external chain of thought, the internal chain of thought, the tool use, and we had here problem solver or Lean 4, some beautiful instruments here to have here some logic derivations. And today we ask ourselves, you know what? Let's start where we left off, and what if we could build a surface manifold on those internal chain of thought subspaces? So our lava stream here, the internal chain of thought, is not just an irregulated, chaotic fluid system, but if we build here a mathematical subspace or a manifold where there are some limitation imposed on the chain of thought generation by the LLM. Does it sound interesting? Absolutely! And here we have at October 24, 2025, DAG-Mathematics Graph Guided Mathematical Reasoning in LLMs. And I know that a lot of my viewers said, hey, can we have please a mathematical reasoning model, not those simple explanations here? Well, this is here the video for you, and welcome. We will introduce here the logical closeness of a directed acyclic graph in the generation here of chain of thought construct, and we want to optimize our chain of thoughts. So this is here a positive video because we want to provide new solution as here by those great people. Now I'm going to tell you the solution. You don't have to watch the video. I'm telling you, the core innovation of this paper, and this is a beautiful paper, you have to read. And if you watch this video, you will smile the whole way through, is we're modeling the chain of thought sequence at the step level as a direct acyclic graph. Isn't this beautiful? Isn't this simple? I know. So you know that in general, our LLMs demonstrate a strong performance here, and we thought that a chain of thought is the solution to everything, no? But now the authors tell us yet it remains unclear, and we're all shocked here, whether the success of our chain of thought here stems from a searchability, from route procedures, or rule-consistent reasoning. And we all think, yes, it is the rule-consistent reasoning that is emerging as a phoenix now out of the ashes here of non-thinking and non-reasoning. By the way, you know English is my third language, so I had to look up what the hell is a route procedure. Those are methods of learning based on repetition and memorization. So repeating facts, formulas, sequences until they are in the memory. So this is just something that we have in our memories encoded. But we want not to have the search. We don't want to have memorization effects. We want to have the pure crystal emergent reasoning, no? That comes up here, and this is a generalization we're looking for. And now the authors say, hey, we propose modeling now this chain of thought in a very specific way. Now we have here as a certain rule-based stochastic process over a directed acyclic graph, where, yes, you love here the mathematical links here to graph theory, where the nodes represent now intermediate derivation states, and the edges encode now the rule applications. It sounds so simple, but you have to have this idea, no? So here we go. DAG-Math, a new framework, provides here balance between the free-form chain of thought, here our lava stream, And the formal proof systems like Lean4 or whatever you have here, offering some actionable diagnostics for LLM reasoning evaluation. And it is here in between, somewhere in the middle here, we have a new surface. So interesting what current research in AI, what people are examining and trying to find out. So what they say, phase one is, so we build a task-specific DAG for a step-level chain of thought. So what we have for any, now when we go here, not in a general syntactic language case, but we go for mathematical problems because they are so simple to validate. No? The result is true or false. That's it, full stop. So we have here a limitation only to the mathematical space here. A chain of thought step is a natural language derivation of a new conclusion from prior information. Of course. So therefore each step has two components. No? We have, it's a graph, guess what? We have an edge and a node. The edge is the justification. So this captures here the inference that leads to the step's conclusion. The edge explicitly encodes now the logical mathematical dependency on the problem statement or on the previous steps, making now the reasoning chain transparent. How beautiful is this? We don't have anymore the autoregressive next token prediction. In the node, the conclusion is easy. No? The node represents the step's conclusion, the state or the value derived from the edge logic and the parent nodes. So as you see, a single chain of thought step, a single step of a chain of thought can be viewed here as a node edge decomposition. And we can have a look at this. Simple mathematical problem. You see here the blue part corresponds here to the parent node. The green part is here the new conclusion. And guess what? The orange part is here the logical reasoning, our edge construct. Now, they say, but it's not that easy. We say, come on, task-specific DAG, we already have some studies, so we're already building on something, and they say, we define our directed graph as this. Our graph is here a set of vertices and a set of edges. Now, the edges are directed edges, but now the set of the vertices we have three different, if you want, categories. No? We have the set of source node, so the nodes formulated solely from the input prompt. Then, guess what? We have the output vertices, nodes, denotes the set of sink nodes, the node with only incoming edges and no outgoing edges corresponding here to the final answer. And we have correct and incorrect one. And then we have all the intermediate nodes. It is simple. I told you you're gonna smile. If you want to see an example, this is it. Task-specific DAG from Llama 3.1. We have here simple here. We have here, if you want here, our input nodes, V1, V2, and V3. Then here, from V4 to V9, we have our intermediate nodes, and then we have two output nodes. One is the correct one, V11 is the incorrect one. And you can go here now, logically, and see exactly what is happening here to our mathematical logical sequence. So it all begins here with the logical presumption that a mathematical chain of thought reasoning process in an LLM can be modeled as a rule-based stochastic process over a latent directed acyclic graph structure. If this is true, then we can build whatever we want. So this framework now formalizes this chain of thought in two phases. Phase one defines here task-specific DAG as the search base, with nodes representing here the derivation states and the edges encoding here the rule applications. And a phase two that generates now the chain of thought trajectory over this DAG via stochastic transitions. So now we have something beautiful. Now we have the autoregressive next token prediction from the LLM, plus we have a strong implication here from stochastic transition, and we have a directed acyclic graph where we have defined a specific framework. You see how we are having here a congruent framework that is now converging towards a more logical understanding of the sequence. So rather than starting here with multiple free-form chain of thought traces and attempting here post hoc decomposition into a DAG, that would be one possibility, but maybe not the most intelligent solution, the authors introduce here the DAG-Math format to make here the DAG structure explicit during here the next token generation. As I told you, the format structured here each chain of thought step as a triplet. Of course, it's a graph. What else, you might ask, no? So we have an edge, the justification, then the parent node, and the node with the conclusion. Great. So our LLMs, and we're going to test out some of our LLMs, are prompted, maybe via a few shot or a three-stage method I'm going to explain in detail, to produce now chain of sort trajectory directly in this format, which inherently embodies now the DAG structure without requiring a separate decomposition. How beautiful is this? How simple is this? So let's see this. This three-stage prompting method here is a structured approach used here in this DAG-Math framework. And we use it here to build, of course, we have to have a benchmark that we compare the performance of our LLMs against. No? We have to have the gold standard benchmark. So let's build this. And they said, okay, we built here the gold standard benchmark of close to 3000 DAG-Math formatted chain of sort trajectories. So this is here perfect. This is the perfect reasoning if you want. How they do this? Well, they need a lot of little LLMs. The method employs your LLMs like GPT-4, the mini for the stage 1 and 2, and QN235B. It's a mixture of expert model with active 22 billion. Thinking for the stage 3, or you go with a GPT-5, whatever you like. Plus, we have here some evaluation for the correctness and for the logical closure. And logical closure will be very important here in our future ideas. So let's start with stage 1. The node set generation. So generate a verified set of nodes from the problem and its correct solution, ensuring each node is a single sentence mathematical or logical assertion. So one primitive action per step to normalize granularity, and we have here this data from the Omni-Math dataset. But the authors decided to only go, there's a difficulty level from 0 to 10, and there's a difficulty levels less than 6. Okay. So each node, a single sentence. Okay, mathematical logical assertion. So let's do this. So GPT-04 Mini is prompted in a supervised setup, providing with the problem statement and the original solution. From our dataset, Omni-Math dataset, it instructs the model to rewrite rough multi-step solution into a detailed structured format. Here we have some condition, great. And they give us here the explicit prompt. So the prompt for the stage 1, here you have it, this is the task. You say to tell the AI, hey, you're an expert in mathematical logic and reasoning, your job is to take, yes. And here each step, here you have all the condition, beautiful, refined step-by-step answers, great. Stage 2, the parent assignment. No? Assign a minimal direct parent to each node to form an acyclic graph, ensuring here a logical closure relative to the sink, no unclosed intermediates. So again, we use here our 04 Mini prompted with a verified node from stage 1, formatted as JSON. And here you have the explicit prompt for the stage 2, the instructions for the step dependency analysis. Beautiful, beautiful, beautiful. Stage 3, the edge generation, the last thing for the graph. No? Generate now the justification, the edges, explaining how each node derives from its parent nodes, ensuring no new facts are introduced. Simple, yeah? Now we take a little bit more powerful model like QN235B, thinking, promoted here with the parents node from the stage 2 as JSON, and then we have these details. Here again, they give you the explicit prompt for the stage 3, the role and objective, and all the instruction. If directed to dependent steps, so this is now really a detailed instruction what to do. They give you even here a demonstration example. This is really nice. It goes on, it goes on, it goes on. The style requirement, the self-validation, the stop conditions, the output format here, and another JSON output example. Great. If you want, you have everything already on Hugging Face here, the DAG-Math formatted chain of sort dataset. Great. And a GitHub, of course. So, to test now our LLMs that you have against this DAG-Math golden benchmark, the set of close to 3000 gold standard logical closed DAGs derived here from the Omni-Math problems, how we do this? How do we test our elements? No? Involves prompting the LLM to generate here a structured chain of sort trajectory in the DAG-Math format, of course. For the benchmark problems, then evaluating those outputs using here the framework metrics. And you have the classical posit 1 metric, but we also will build here new metrics like the perfect reasoning rate or here, I will show you in a second. So we have 5 steps here to compare our LLMs or your LLM. Prepare the test setup. You have here the benchmark dataset on Hugging Face, I've shown you. Then you prompt the LLM to generate here the DAG-Math formatted chain of sort trajectories. You parse and extract the trajectory-specific sub-DAGs. You evaluate each trajectory and subtrajectory for logical closeness and correctness, and you compute your multiple metrics per problem and aggregate the solutions. If you want to have your older parameter, here we go, logical closeness and perfect reasoning. How is it defined? We say that this is logical closed if we have this condition, or we talk also about here the perfect reasoning chain of thought trajectory, and then we have the mathematical reasoning ability, and here you have the new perfect reasoning rate of an LLM, and then we define here the overall mathematical reasoning ability of an LLM over a certain distribution. Real nice new parameters, and they are real powerful. And I will show you why they are so powerful if we compare them to a parsit one, for example. Okay, so we do have the gold standard DAG-Math benchmark, beautiful, and then 5 representative graph level statistics. What we are looking now at, and we try to come here to the benchmark conclusion, what we're looking at. In this graph, the total number of nodes, the total number of edges, the graph density, the maximum in degree, and the maximum out degree nodes. So let's have a look at this. Here you have the number of nodes, the number of edges, the graph density, the maximum in degree, maximum out degree, and probability densities on the y-axis. And color-coded, you have here the complexity from very simple, very easy here to 6, not 10, but 6 here, the most complicated. Great. Now I have to tell you, looking at this, I said I see nothing. I'm not able to interpret this. So luckily, the authors provide us here with the insight. If you look at this for several minutes, you find out that there are 3 hidden messages. First, more nodes and edges with the heavier tails. The distribution of the number of nodes of the number of edges shift noticeable to the right and develop heavier tails, indicating that the harder problems produce larger graphs, which was to be expected, honestly, while simpler problems yield much smaller graphs. Okay, would say nothing special, no? Sparse structure, this is 50-50. So the graph becomes sparse when the problem's difficulty increases. Harder reasoning produces broader, less connected graph structures, reflecting here a modular sub-reasoning where semi-independent chains are later to be combined. Subtask. So it works that if we have a hard reasoning problem, then this deconstruction into lower complexity subproblems, okay, seems to be working, less connected structures, reflecting a modular sub-reasoning. Okay. But now something interesting happens. The logic complexity reflected in the maximum out degree now is interesting. As the difficulty increases, if we move more to the right of the x-axis, the distribution of the maximum in degree and the out degree shifts rightward with heavier tails. But the maximum in degree grows slowly, suggesting most steps rely on few inputs, whereas maximum out degree rises much more sharply, indicating that certain key steps support multiple inferences. What does it mean? Simple. This implies that the logical complexity scales primarily through branching rather than aggregation. So the graph branches out in a lot of subgraphs if it gets more complicated, but what's not happening is then the aggregation step. And if you look at my video where I showed you GPT-5 and the limitations of GPT-5, this is exactly what we analyzed more than a month ago in the performance of GPT-5. Yeah, average in and out degree remains 1.3 across difficulty levels. Great. So just to make sure what, if you want, the core essence of the finding was, the LLM should be able to decompose problems into lower complexity subtasks, be able to track longer logical dependencies and complexities. We are talking about a chain of sort trace sequence. But then, and this is the most important thing where it seems to fail, recombine now all the intermediate branched out results back to have a convergent answer to solve now the challenging problems effectively. And I say, okay, let's do this. Let's evaluate the mathematical reasoning ability. And this is here a new benchmark factor. And we evaluate 5 LLMs, Gemini 2.5 Flash, Flash Lite, GPT 4.1, 4.1 Mini, and Current 3 30B. Beautiful. As I told you, to evaluate this now, and we have not trained our models for this, but we want to tell them what you have to do. You have to build here not just an autoregressive chain of sort sequence, but you have to build here a formatted DAG-Math formatted chain of sort DAG format structure. We have to provide, of course, few-shot prompting and in-context learning. So we guide here this with some examples. They give us here the complete prompt. Instructions for DAG-Math formatted chain of sort generation. To roll an objective, all the requirement, each step has exactly 1, 2, 3, 4, 5. We go on. Yes, global constraint demonstration. The gold standard demonstration examples. If you have anything else, then here the math data set. If you work here in logic, if you work in chemistry and physics, you have to insert here your gold examples. And of course, they have to build some bad examples because you want to filter this out. Great. And then this is it. So if we do this, if the authors already did this for us, what is the result? 3 different benchmarks. We just look at AIM25. You see immediately for all our 5 models, there is a massive discrepancy between deposit 1 and R. R is here our mathematical reasoning ability. This is such an important factor. But look, compared to deposit 1, the success rate, this is minuscule. This is 52 and this is 17. 35 percentage points less. What's happening? Why is the mathematical reasonability so low compared to our current known PASIT 1 benchmark data? They did an explicit analysis. Please read the paper. There's a lot of additional mathematical models and interpretation of this data. I just give you here the most important insights. And they also had here the calculation here, the area under the curve. And they said, okay, if we have the PASIT 1 here on the left side and here the mathematical reasoning ability here at the end of the right side, how is now AOC for our 5 things? And this is great. And they came to the conclusion, beautiful, that search inflates PASIT 1 via an exploratory branches. Now this is interesting, and this would explain what we see here. 50, 40, 30, 30, 40, compared to 17, 15, 16, 20, 15. Why? And the author said this confirms that this parameter that we use PASIT 1 is not the parameter that we should use if we really want to understand the mathematical reasonability of a chain of sort generated by our LLMs. And they have these 5 LLMs, but you see it's a cross-cut more or less the same. And they say now that search inflates here the accuracy, PASIT 1, without boosting the reasoning. Now, this is something that is strange because I thought, hey, if we have an intensive search in the solution space, no? If we have a strong exploration of all the possible paths, it must here boost the accuracy, no? And boost the reasoning capabilities. And they argue it inflates only the accuracy because, by luck, we find the right reasoning path, but it is not boosting here the real mathematical reasoning ability of the LLM, if you exclude luck. So I looked at search. What does search really mean? Search refers to a search-based strategy employed by by any LLM during the chain of sort generation, as opposed to the pure rule-consistent logic inference. So this preprint formalizes here the chain of sort as a trajectory over a directed acyclic graph where denotes the derivative states and the edges are the inference rule. We know this. And now search is modeled as an exploratory sampling over this DAG, involving the stochastic transition that branch into multiple possible paths, trying alternative derivation, trying different hypotheses, or exploring sub-problems or subspaces or whatever. So this search that we are looking for in reinforcement learning as an explicit, if you want, training objective, now we find out this search can help in one parameter like PASIT 1, but it does not improve the reasoning ability of the LLM. posit 1 is the fraction of independently sampled chain of thought trajectory that end with the correct final answer at the sync node, that is the correct sync node, but ignoring the logical coherence of the intermediate steps. And this hurts. This should not be the case. And the paper now, the preprint, argues that the search inflates here this metric by increasing here the probability of reaching a correct sync node through exploratory branches without requiring rigorous logic. This is, if you want, by pure chance. Now you might say, okay, why not? This is all try and error. But we want to improve our systems. We want to improve here the chain of thought reasoning abilities of our LLM. Therefore, we ask now, how can we improve the training of our LLM for the next generation? We want that the next LLM generation is much better in reasoning. So the authors found that this inflation occurs for two interrelated reasons. Of course, we have now an increased coverage of possible paths. We just let the system run wild and try out all different possible paths in a high-dimensional space. But this can become very expensive very fast. So if you just allow the LLM to sample here a wider range of trajectories over the DAG, in the stochastic process the transitions are non-zero only for the valid next nodes, but with the diversity model can pursue multiple directions, may lead to the correct sync accidentally, even if the trajectory include irrelevant or incorrect intermediates. But also luck in finding the correct path. And I think, this is the primary mechanism here that they found. So, you can be lucky. We are talking here about statistical system. This is an autoregressive system. You can be lucky that, at the very first or the first 10 runs, it finds the correct path. It finds the optimal path in this network. But the chances are really, really minimal. So how can we improve this? Because we want to have a solid path to success. So search inflates here the posit 1 not just by luck, but also by enabling recovering from flawed branches through recombination or correction, like in DeepSeek R1, masking here underlying reasoning gaps. So now we say, hey, what was okay with DeepSeek R1 that we said, hey, if the AI understood that it came to a dead end in its reasoning, you just go back until you are again on a green path, and then you say, okay, now I branched somewhere else. But we say, hey, we want that we have, a mathematical complete logic enclosure on a mathematical surface that is really giving us only the valid path forward. We don't want here, like in a tree search or whatever, to just try an error. We want to find the right way. And there must be a solution that supports the AI to find the right way. So this underscores the need for metrics like here, the PRR, which penalizes such exploration, forward, going back, have some correction. It's not the time anymore to play around. The LLMs, if you want, hike here the complexity surfaces of DAG via the stochastic process, but do they follow the most logical route, or do they just wander aimlessly until the luck strikes them? And the authors, and this is now here the final result, uncovers here the hidden truth that the high accuracy that sometimes we achieve with our model doesn't always mean that there's some real rigorous reasoning going on in our chain of thought reasoning. And they invented here this new term, the logical closeness, a beautiful new parameter to measure how tightly a chain of thought trajectory hugs here the DAG structure. Think about this here as a particular surface of a particular manifold here without dead ends, and a perfect reasoning rate, PRR, which rewards only those paths that are both correct and logically pristine. Therefore, we are faster in our training here with reinforcement learning, and we have a better success rate. So you see, understanding the failure points in our current models, we understand how we have to train the next generation of AI models to have better results. And we just learn by understanding what is currently not working. Yeah, and the authors tell us, after we built here the benchmark of nearly 3,000 gold DAGs, evaluated all the top models and tough mathematical problems and whatever, true perfect reasoning of our AI systems remained elusive. And as I already told you, this shows us how we have to rethink how do we train, how do we post-train our large reasoning model for the next generation. So let us end here with a positive outlook. Model improvement. We have to incorporate now DAG structures into the training, like reward models for logical closeness during the fine-tuning, or graph neural networks to encode here the dependencies in a much cleaner way. For instance, in reinforcement learning from human feedback, just add the process rewards for a closed DAG. This is such a simple code to implement, but I'm really looking forward how much it will improve here the overall system performance, reducing here exploratory overhead for each and every run of our AI system. You see, sometimes a solution can be so simple if we really understand why it's not working. So therefore, I try to show you in my videos what are the current limitations in our LLM systems, and then how can we go forward and how can you find solution to improve the performance of those systems. What a beautiful paper. What a gorgeous paper, DAG-Math, Graph-Guided Mathematical Reasoning in LLMs. There are a lot of mathematical theorems and proof I have not mentioned in this video. Please go have a look at it yourself. But just what they do. You remember, we started with LLMs that operate here autoregressively, predict the next token, conditional on all their prior context. And now the next generation of tokens is constrained now to only valid logical transition over a particular defined directed acyclic graph, ensuring that only the logical feasible steps are possible. Such an easy solution. We don't say, hey, there is here a 1000 dimensional solution space, just go and have fun and maybe you'll find the right path. But we constrain this to a subspace and we tell it, hey, we found all the logical elements here for a chain of sort assembly, a generation, and you are only allowed to walk here on a submanifold over the DAG structure that we built for you, and therefore you only can reason here with correct logical terms, and the dependencies should be correct by definition. But of course, you have to build your DAG, and this is not an easy task, and we did this here only for simple mathematical problems. I have no idea how you could do this here in non-formal linguistic complexities. I can imagine this in medicine, I can imagine this in law, I can imagine this in theoretical physics, where we are very constrained and very close to our mathematical apparatus. But the more you come into the creative dimension, I think, wow, this will become really a challenging task ahead. So, as I told you, create here a manifold, a restricted subspace of allowable path, preventing arbitrary or circular derivation in the building up of our chain of thought reasoning trace. I hope you enjoyed it. I hope you had a little bit of fun. Why not subscribe? Maybe become a member of my channel. And I hope to see you in my next video.